going to go U-Substitution, and hopefully this is a follow-up to something you've already done a little bit of, but there's a chance that this is not your most familiar topic. And things you want to ask along the way are any kind of little pieces. Once you get the steps and the basic fundamental idea, then you can kind of work your way up to tougher problems. In here I talk about something called pattern recognition. That's kind of when you're all done doing a lot of U-substitution problems, there is a pattern that goes to it that you want to start looking for, a way of doing it without quite as much work, some steps that are pretty consistent. So keep your eye out for the pattern that goes with it, because eventually we'll kind of do them by sight and a little bit quicker. But in the meantime, feel free to do it the long way as often and as necessary as possible. The big concept is what you're doing for U-substitution is an integration technique, so it's going to happen down here in example 2. And it is a matter of actually taking a former chain rule derivative and undoing it. So I'm going to do the chain rule right here on this particular problem. So tangent of e to the 4x squared. And if you remember your chain rule, it's the derivative of the outside, and the derivative of tangent is secant squared. And then you leave the inside untouched, so you have that e to the 4x squared intact inside. And then immediately outside of that, you're going to multiply by the derivative of the inside, and the derivative of e to the 4x squared is another chain rule. And the derivative of e to anything is, you rewrite it, so e to the 4x squared, and then also times the derivative of its inside, in this case the exponent 4x squared. So that would be times 8x. Done. So that behemoth is our derivative. Now if you look down below, that is what we're seeing in the integral over here. So to say, hey, what's the integral of that would simply to be the tangent of e to the 4x squared. And then the part, remember when you're anti-deriving though, is that we could have had, there could have been, say, plus 100 at the end here. And when I took the derivative, it would be gone. Okay, so I wouldn't have it here, so the derivative. So instead of 100, it could have been any number. I'm going to put a plus c here for that antiderivative. Okay, so just fundamental theorem, the idea of derivatives and antiderivatives, they undo each other. Now this, what would it take? How could you, in some shortcut manner, go from this integral here and find a way to the tangent of e to the 4x squared? And that's where U-substitution kicks in. You recognize that there's a chain rule going on, that there is some internal function that you can call u. In this case, it's this thing right here. U is usually like an inside a parentheses part of your function, or an exponent or a denominator. And here's the qualification for this inside u that's necessary. We need a function on the inside that we see a multiple of its derivative show up on the outside. And if you notice, the derivative of e to the 4x squared was e to the 4x squared times 8x. Do you see that multiple, that derivative right there? That means e to the 4x squared is a candidate to be your u. So you want to look for something that's internal and whose derivative, or at least a multiple of it, shows up outside being multiplied to the rest of the function. There's U-substitution in a nutshell, but they obviously get more complicated. So think of it as you're always looking for that inside function where the derivative of it is showing up outside, even within the integral. So you see the sum g of x, and right next to it you see a multiple of g prime of x sitting right outside of it when you're integrating. What we'll do is we'll call that inside function, that g of x, we'll call it our u, and then we'll do some work with it and make it happen. You guys did this before. I'm sure it's a distant memory, and it was also really brief, but at least that's kind of maybe tapping into a mild memory that you had once upon a time. Now there's a whole lot of verbiage going on here that we can go back and look at later, but in the meantime I actually want to just jump to it and get down to an example. And that particular example here, so let me show you why this, how this kind of works. I look at an integral like this, and if I see an inside, which in this case is a parenthesis or parenthetical piece, and if you look outside, the derivative of x squared plus 1, if you see a multiple of that multiplied right outside, that means this is a U-substitution type of integral. So u equals x squared plus 1. And what happens is we do this process where we are going to rewrite this integral as an integral of something with respect to u. And the technique is to get this somewhat messy integral to look like a rather simple integral in terms of u, do the antiderivative, and then when we're done, we put u back. We replace u with the contents that we substituted. So, in this case, put u back as what is it, x squared plus 1. Okay, so this is a temporary condition. Oops, I can't write. That's supposed to be an x squared. As x squared plus 1. That's kind of the short end of the story. Now watch as I walk through this. If I pick the u, you do take the derivative of it. I'm going to call it du dx. Okay, that's that function, or the what we call integral. It's the differential notation. The mathematician behind it we'll get to a little bit later. But du dx would be 2x. Okay, so we're doing derivatives again. And then the way this works, you actually combine the u's on the left and the x's on the right. So I'm going to rewrite this differential as du equals 2x dx. Okay, and that sounds funny, but differentials are actually quotients. So you can multiply both sides by dx, and that is perfectly fine. It is actually part of why integrals have that dx in their expression anyway. Okay, so watch this. What I'm going to do, and very color-coded, is I'm going to start replacing stuff. These are equations that I just wrote that I'm going to use to rewrite my integral. So these are my replacement equations, the substitutions. So we're going to replace expressions of x with these, this right here. And if you look up in our original equation, I'm going to use blue now for this one. I'm going to take out, see this 2x dx right here? I've got one in my original integral. I'm going to replace that with du. Okay, so I'm going to do it right above it. So I'm going to kind of parallel these guys. So that's going to become du right there. Then I'm going to pick another color. Let's go purple. I'm going to take out that x squared plus 1 that you see right here. I'm going to replace that with u. Okay, so the equation on the left. So this will become u. Now it's still squared, and it's still an integral. Now look at this. We just rewrote with these replacements the really messy looking integral, and now it's just the integral of u squared du. Remember I told you it would be a really simple integral with u involved, in this case u squared. That's it. That's the u-substitution. Now what we're going to do is actually conduct that integral of u squared du, and that is 1/3 u to the third, of course, plus c. And after we've done that really simple integral, now we put our u back the way it was as x squared plus 1. And that is the end. The integral that I started with, the relatively messy looking one, like that, is actually equal to 1/3. Now we put the u back, x squared plus 1 cubed plus c. Done. So the u-substitution is to come up with an easier integral, replacing with these equations that I have in green up there. And we do it over and over and over again. So to what extent you're comfortable with this, if you notice that this is kind of patterned and consistent, let's do a bunch of these and then start to see what pattern you pick up and see how it probably gets pretty easy with time. Okay, so we're going to go to another one, number 4. If I look for the inside function, okay, something in parentheses, some exponent, some denominator, we're going to see examples of each pretty shortly. That's going to be your u, and it also has another qualification. The derivative of this is 2x. Do you see a multiple of 2x outside being multiple? And it is, yeah. 3x actually counts as a multiple of, that's a terrible way to spell multiple of 2x. Okay, so we have that. This is good. This basically says I definitely want to pick x squared plus 1 as my u, and then you go about deriving it. Okay, we get 2x, and then you take and multiply both sides by dx because you want to separate the u's and the x's because we're replacing the equations, x equations with u equations. Okay, so we get this. These are our equations. Now the only problem is, remember last time I was able to replace a whole chunk with 2x dx? Well, look up here. My equations are a little different this time. I'll highlight them. Oops, let's go green. Okay, this 2x, I don't have a 2x, I have a 3x. Well, I can turn that into 3x with a little bit of algebra help. A couple ways to think about it. You can multiply both sides by a fraction, but one is I usually just divide away that 2 and kind of clean things up. So I'm going to put 1/2 du equals x dx, okay, and then go back in and multiply both sides by 3. So it's kind of a two-step process, and I get 3/2 du equals 3x dx. It's a little algebra manipulation, but here's what I wanted. I really, really, really wanted this to be something that can replace what's up here in my equation. That 3x dx in the original, I can replace with the 3 halves du. And I'm going to parallel it. See if you can follow this. And you can write it any way you want in your notes. Maybe I'll do it off to the side. Okay, here's my original. And right here, 3x sine, correct? Yep, sine of x squared plus 1 dx. So the first thing to replace in green, and I'll keep these nice and coded, the 3x dx, you could rearrange that a little bit and put those at the end. You can manipulate these. This is all a product inside. So you're welcome to flip it around if that helps you. Okay. That gets replaced with 3 halves du over here on the left. So I take out that whole thing and replace it. So here goes. 3 halves du replaces what was formerly 3x dx. Those are replacement equations. The other replacement I can do really fast is remember that x squared plus 1 is actually can be u. So we're going to do sine of u. And you integrate it, and you know you're done when there are no longer any x's and you have only expressions in terms of u. So I look at this and go, is this easier than what I started with? Because that's the idea. You replace them all to get something simpler, and it is. That 3 halves, that's a constant. You can pull it out front. We're just taking the integral of sine of u, du, and the integral of sine is cosine. Derivative of cosine is negative sine, so it's negative cosine. So it's negative 3 halves, because you carry that 3 halves over. Cosine of u plus c. And the fun final step, of course, is we actually have to put the u back because we're actually evaluating the integral with x in it. So you want to make sure you put at the end what u replaced, you have to put it back for u. So x squared plus 1 goes back in. Bam, and we are done. Okay, so that's a good stopping place. That's like 2 really nice, clean u substitutions with the same u's in it. Part 2's coming, but you can kind of take a deep breath and check what you've got going, and we'll pick up in the next video.